Welcome to this video lecture on the simply typed lambda calculus. In this video, I will introduce you to the simply typed lambda calculus, and I will explain the relationship of the simply typed lambda calculus to logic. This relationship is sometimes called the Curry-Howard isomorphism. The simply typed lambda calculus was introduced by Alonzo Church in 1940. It is a very simple programming language, but it's nevertheless very important and very useful because it is the core of many modern practical programming languages. For instance, OCaml, Haskell, Lean, and many more. The simply typed lambda calculus consists of sort of two ingredients, the types and the terms. Types are, for instance, atomic types, but also composed types like the product type A times B, if A and B are types, and the function type A arrow B, if A and B are types. Terms can be seen as inhabitants of types. It's important that every term has exactly one unique type. So, in the following, we will mostly talk about typing, and we will write tiny a colon capital A to say that tiny a is a term of type capital A. What are the types of the simply typed lambda calculus? Well, firstly, we have atomic types. For instance, we will have type variables, and we have the constant type 0. But then we will also have more complicated composed types like the function type. Here, if A and B are types, then we can form a new type called A arrow B. We have the product type. If A and B are types, then A times B is also a type. And lastly, we have the coproduct type, or also called the sum type. If A and B are types, then A plus B is also a type. The simply typed lambda calculus is just the core of a useful programming language. In practice, in practical programming languages, one would have more type constructions and more base types. One would usually have a unit type, which is a type that has exactly one element. One would have a type of natural numbers, type of booleans, but also type constructions like lists, which are type constructions where one has an input, a parameter. For instance, if A is a type, then list of A is also a type. For the purpose of this present discussion of simply typed lambda calculus, we will only discuss these four type constructions, the atomic types, the function types, product types, and coproduct types. Let's look at a few examples of types. Here, the first example is a function type from A times B to C. So we put parentheses around here to indicate the correct parsing of this type expression. The second type is also a function type of functions from 0 to B plus C. And lastly, we have a type that uses all of the complicated type constructions times, arrow, and plus. So this is the outermost type construction. The root of the parse tree is the plus here. And we have two arguments to the plus. The left-hand side is this complicated type expression A times B arrow C, and the right-hand side is the atomic type D. To make writing types easier, we introduce a convention, a parsing convention. Namely, we say that the times construction binds more tightly than the plus construction, which in turn binds more tightly than the arrow construction. With this convention, we can omit some of the parentheses in these examples. For instance, we can write the first example as a times b ROC without any parentheses, because by convention we put parentheses around the more tightly binding construction, which is the times. The second example can be written again without any parentheses, 0 RO b plus c, because by convention we imagine parentheses around b plus c, because the plus binds more tightly than the arrow. In the third example, we can omit one pair of parentheses around a times b. This is actually the same as in the first example. So a times b ROC, it will be read as a times b with parentheses around and then ROC. But we cannot omit the parentheses around the left-hand term a times b ROC, because if we were to omit these parentheses, the expression would be read as a times b in parentheses RO c plus d in parentheses. So without any parentheses, this term would be mainly an arrow rather than a plus.